Hello, everyone. This is Paul Rodden, and I want to welcome you back to the Hydrogen Podcast. I have a very special guest for the show today, and what he's going to talk about is a game changer for the hydrogen industry. There was a hydrogen project started in Texas in 2020 that utilized the H2 at scale funding from the U.S. Department of Energy. The project's goal was to bring hydrogen industry leaders together to design, build, and operate the first dedicated renewable hydrogen network. The project will also be able to leverage Texas's extensive resources, which is wind power, solar power, underground salt dome storage formations, hydrogen pipelines, natural gas infrastructure, international port operations, and a large concentrated industrial infrastructure to help in the creation of this network. As the project is coming to its conclusion, I feel that it's vitally important to understand what we've learned from this, and I asked Mike Lewis, the head of the H2 at Scale in Texas and Beyond program, to come on the podcast and discuss its importance. I think what Mike and his team have done is successfully model the future infrastructure requirements for the hydrogen industry, and based on everything I've heard, they have a pretty good blueprint. So enough of me talking, let's cue up the theme song and dive right into the interview.
So the big questions in the energy industry today are: how is hydrogen the primary driving force behind the evolution of energy? Where is capital being deployed for hydrogen projects globally? And where are the best investment opportunities for early adopters who recognize the importance of hydrogen? I will address the critical issues and give you the information you need to deploy capital. Those are the questions that will unlock the potential of hydrogen, and this podcast will give you the answers. My name is Paul Rodden, and welcome to the Hydrogen Podcast.
Okay, welcome back. Today I'm talking with Mike Lewis. He's the principal investigator and a senior research engineer at the Center for Electromechanics at UT Austin. Mike has over 20 years of experience in advanced research and technology development and is currently focused on alternative fuels for transportation and stationary power applications, with a large focus on hydrogen power and energy systems. He's spearheading the H2 at Scale in Texas and Beyond project, and in my opinion, his research has led to some interesting breakthroughs for the hydrogen industry. Welcome, Mike. It is great to have you on the podcast.
Thanks, Paul. Thanks for having me. My first time on the podcast, so I'm very excited to do this. So thanks.
So if you can, tell us a little bit about your background and what led you to oversee the H2 at Scale in Texas and Beyond project.
Sure, yeah. So I'm a mechanical engineer by training, got my undergrad and master's degree at the University of Texas here in Austin. I've been with the Center for Electromechanics here at UT for all of my career, I guess over 20 years now as a researcher. Even started here as a student, as an undergrad student, kind of through a co-op or internship program with the university. But in the mid 2000s, around 2006, I got assigned to our first hydrogen related project that installed the first hydrogen fueling station in Texas, and really the only one ever installed in Texas if you discount ones for forklifts that are operated by Walmart, H-E-B, others in the state. But as far as a kind of a vehicle-sized fueling station, primarily the only one that's ever been in Texas. Along with that came a bus demonstration project. Having that station in place fed a lot of our ongoing research since then, over the last 15 years at this point. Much of that was focused on different vehicle technologies, doing a lot of vehicle demonstration projects, developing first of their kind fuel cell vehicles. We demonstrated a couple of transit buses along the way through the Federal Transit Administration funding, part of the National Fuel Cell Bus Program, and those were operated with our local transit agency. More recently, we developed the first prototype parcel delivery van that ran on a fuel cell hybrid powertrain. This was a Department of Energy sponsored project. We worked with an OEM that was working on electrifying that vehicle platform during phase 1 to build a prototype version that ran on hydrogen. And now in phase 2 of that project, that company, Unique Electric Solutions is their name, is building 15 more of those vehicles.
Wow.
And they're being deployed and operated by UPS in California, Southern California primarily at this point. But along the way, beyond vehicles, we also found ourselves applying the Center for Electromechanics knowledge of motors and generators and electric machine designs to other things like compressors and expanders for hydrogen infrastructure, right? It's not just about the vehicles. Along the way, we realize there's the fueling stations need work and advanced research. And historically, the Center for Electromechanics had done a lot of electric machine design and work, and we tried to apply that to see how we can improve the drive mechanisms for compressors, as well as expanders. And for the expander, we would be using that to pre-cool gas at a fueling station before it's dispensed into the vehicle. Those are projects that we've been working on for several years now, that all started with an ARPA-E grant for actually a natural gas compressor, not a hydrogen one. But those were in partnership with Gas Technology Institute, which has been a great partner throughout all of our hydrogen research. They actually were the ones that helped us install the very first fueling station that I mentioned earlier as well. But that has kind of all led us to this point with this hydrogen at scale project, right? So just kind of that fundamental background and different aspects of hydrogen technology and trying to bring it together into this hydrogen at scale ecosystem, or proto hub, as we're kind of more recently terming it. How does all the infrastructure come together, different end users, how do you put it all together? What does this hydrogen hub look like? Effectively, when we wrote this proposal, we were proposing a small scale hydrogen hub before hydrogen hub funding became available, or anybody was talking about hydrogen hubs.
That's incredible. I mean, just being in Texas, I love that all of this is getting developed here in state, and that you're able to just push this.
Oh yeah, tell me about it. I had plenty of projects that were deployed in California along the ways, and so bringing one to Texas was definitely part of our motivation when we proposed for this H2 at scale project.
I'm really just so thrilled that you're able to do that. So if we can we do a deep dive into the project? What is H2 at scale and in Texas and beyond, and how did the project come together?
Well, sure. The project came together through a Department of Energy funding opportunity announcement. Over the last few years, they, every year, every funding cycle, they sponsoring H2 at scale demonstration projects of some sort, and people were doing various things. So we responded to one of those in 2019 with that announcement. And with that announcement, they had a focus on, renewable hydrogen generation, also using hydrogen for data centers. So just kind of looking at the feedback, what we saw in the announcement from DOE, got to thinking and brainstorming what we could do for a demonstration project in Texas and at UT Austin. And the demonstration project that we currently have, it will be at the J.J. Pickle Research Campus, which is part of the University of Texas at Austin. It's in North Austin, not the downtown teaching campus. So there's land available, and there's room to do large scale experiments such as this project. And the idea that we had in mind was to try to incorporate as much of the hydrogen at scale concepts as we could into one project, one ecosystem. So in the DOE had funded a lot of demonstrations, but it's, they tend to be kind of do some electrolysis and partner with fueling or something. And we wanted to, we looked at that concept for H2 at scale, that kind of the graphic that most people might be familiar with all the bubbles or circles around it. Yeah. And we're like, what of this can we do on campus? How much can we model this kind of system that's illustrated here in this graphic? So we can make hydrogen from different sources, right? So if we have natural gas, we can put in electrolysis. Can we do that? How do we make both of those renewable for this demonstration project? Just knowing the funding constraints and so forth. Mm-hmm. So for example, we'll be using renewable natural gas with our steam methane reformers that'll be part of the demonstration project. Now that is not trucked in renewable natural gas, but it is including industry partners who are responsible for that industry. And so, for example, it's Waste Management. I think they go by just WM now, is providing the landfill gas, and One Gas or Texas Gas Services is taking that gas onto their pipeline system. And then, of course, that's what eventually feeds our campus. But they're covering the cost of doing all that. That's not a cost to the project. For that. So that helps us on the way. That gets us that renewable feed pathway. On the electrolysis side, we'll have a couple of electrolysis pieces of equipment as part of the demonstration project as well. It would be cost prohibitive to put in big solar arrays and wind farms to power that system. So we are monitoring existing assets and then replicating their power output profiles as as the power feed into the electrolysis equipment. So we get that temporal variation over time and can study how that impacts our ability to generate hydrogen and store that energy and use it later. So that was the generation side of it. But then now, what are our end uses for the hydrogen, right? And there are multiple end uses all throughout industry. But what would be feasible on this campus? Well, vehicles. We can bring in vehicles. So we reached out to Toyota. They're going to partner with us and provide a small fleet of Toyota Mirais for the project demonstration, which is super exciting. And it'll be kind of really the first, beyond forklifts, the first real kind of fleet to be operated in Texas. I say fleet, it'll be on the order of 7 vehicles, maybe 10, not a lot of them. But yeah, it'll be super great. We think that's a very visible part of the project that'll bring a lot of PR and support to it. But the big thing that we had on this campus that I mentioned earlier, the DOE was interested in hydrogen for data centers, is the campus hosts the Texas Advanced Computing Center. And I think this changes probably about every 6 months, but at one time it was the largest supercomputing system in the country. I think every university upgrades their systems every few months, and so that continually revolves, and they may or may not be at this point. So all the hydrogen we're generating here, part of it's going to be used to fuel the vehicles. We'll have dispensers for those, but the majority of it's going to actually be used in a stationary fuel cell power system that'll be connected to the Texas Advanced Computing Center. We're specifically targeting a portion of that computing center that was installed as part of another research project partly funded by the Japanese government, actually, where they were wanting to study DC distribution within data centers to see what efficiency gains could be had there, which is especially important if you think about if it gets tied to solar generation or fuel cells, which are already DC power cells.
Right.
So that particular computing center has a large solar array attached with it, has DC distribution throughout it, and that's the part that we're tying into for this demonstration. So the entire computing center consumes megawatts of power, right? Lots of power. Fuel cell for this project will only be putting out 100 kilowatts, but it's sized specifically for that unit. The peak power draw of that portion of the data center is about 100 kilowatts, pulls on average probably closer to 40 kilowatts. And then there's a 250 kilowatt solar array that supports it. But we're going to tie in the hydrogen generation aspects into all that. Now see how much of that solar can you really capture, how much you can really decarbonize that portion of the data center throughout this project. So we've done some modeling of that, and we can talk about that a little bit later on here in the project. But I think we're finding out some interesting things there.
I love how you're addressing, the traditional utilization of hydrogen, and you've got the Mirai fleet coming in, but also like you're looking into power generation for data centers. I love that application for hydrogen too, because traditionally it's always been those diesel generators as those power backups.
For sure, yeah, and having
use.
Yeah, and we're taking it beyond even backup. There's a lot of talk in the industry of fuel cells replacing the backup diesel generators, but we think there's potential for them to even serve more of a role than just the backup generator. There's opportunities. Well, what we're seeing in the data for that, we'll just dive into it right while I wait, I guess. Looking at the data from the data center over a 1-year period, right? The solar generation, its power consumption. The sun doesn't shine all day long, right? But definitely, when it is out and it is working for you, there's stranded solar energy being wasted, all throughout the year. The data center's not running at that high of power output, so it cannot consume it. So there's an opportunity to store that energy in the form of hydrogen, or maybe even a battery as well, right? Whatever energy storage mechanism you want to look at. We've looked at batteries and hydrogen so far, but then we also notice in the data that that the power center load peaks off and on, right? You'll see peaks of 100 kilowatts, but then it goes down to more of an average or base load, right? In our analysis, there's an opportunity to peak shave with a fuel cell power system, as well as load shift or recapture that kind of wasted solar energy. So beyond the fuel cell being operated just for backup power and replacing that diesel generator, which probably doesn't get used very much anyway, right? Yeah. I don't know the utilization, how often they have to kick those on in a data center, but we see looking at the economics and how much you can save in energy and demand charges and so forth using electrolysis to make hydrogen a fuel cell to provide power, we see an opportunity where it kind of pays for itself. It's not a slam dunk right now for sure.
Yeah.
It's going to take kind of like a 15, 20-year life. It'll kind of break even. You can save money in your total energy costs because you're capturing the excess solar. But then we size the fuel cell to provide, to kind of supplement the grid power, right? So we're not disconnecting the data center from the grid, but we are looking at like a control system for the fuel cell that turns on and provides power whenever the load becomes, say, more than 50 kilowatts at the data center. Yeah. So it can provide that peaking power that you need throughout the day or throughout the year. And so not only are you getting the energy benefit, right, because you're capturing the extra solar energy, but you're also reducing your peak power, so your demand charges, which are a big cost factor for everyone, right? Just about. Right. It's talked about a lot with electric vehicle charging, right? Especially heavy duty vehicle charging, transit buses and so forth. So you start combining those energy savings with the peak power demand savings, and that kind of adds up and starts to pay for the systems over the life of the systems. And then, of course, you have the extra benefit of reducing emissions. And then back to the diesel generator, right? If you size that fuel cell to, be able to do the peak power requirements, in this case, 100 kilowatts, now that's also your backup supply as long as you have hydrogen storage on hand, right? Yeah. So we think there's more utility for that hydrogen system partnered with these data centers rather than just backup power. So that's something we hope to prove and demonstrate as part of this project. I really look forward to seeing those results too. But back to the project, how this came together. It was, how do we incorporate as much of this, the DOE H2 at scale vision and show how this entire ecosystem comes together, right? Mm-hmm. How the systems interplay with one another, right? So beyond just putting in the equipment, we're having to install a small hydrogen distribution network with it, right? Right. Do all the electrical interconnections. How does having a large baseload consumer of hydrogen, such as the data center, help to make the production more economical, more efficient, more effective, such that we have relatively affordable fueling for vehicles, right? So I think that whole ecosystem needs to come together to get economies of scale up and such and make it affordable across all parts of industry or the economy where hydrogen can play a role. But with all that said, that's the project we ended up with. I'll say when I started shopping this around with our partners that became part of the project, both other researchers like GTI, Frontier Energy is our prime on the project, but then a slew of industrial partners. Everyone really wanted to do a demonstration project in the Port Houston or Gulf Coast region of Texas. Yeah. And that makes sense, right? That's where the hydrogen economy already is in Texas, hundreds of miles of pipelines, all the infrastructure's in place. And we'll get to this at some point during this interview too, but that's where all the interest is in Texas today, right? Or a lot of interest is there. So we actually proposed with this project, and this is sort of the beyond part of the project in the title. Beyond just the demonstration, we wanted to take a deep dive into what the hydrogen economy might look like in Texas in the future, right? The clean hydrogen energy economy, right? We already have a hydrogen energy economy. Houston's already a hydrogen hub. Right. It's just not a clean one. So several researchers here at UT are working on developing kind of in-depth techno-economic models. They're kind of, optimization models built on a network model, like a geospatial model of Texas, that's going to build out hubs. Basically, think of a hub or a node as different cities and regions within Texas, allowing them to decide based on whatever industry they have there, whether those industries are adopting hydrogen or not. Maybe they're building out hydrogen pipelines. Maybe it's adding hydrogen generation throughout the state, but trying to let this model kind of smartly help us make decisions on how that hydrogen economy should grow in Texas. And obviously, a big part of it, is on the Gulf Coast, or where we're centering things, and that's kind of the heartbeat of that model where it starts from. But anyway, we added that part into the project scope just so we could be better prepared for, what we didn't know at the time, but it's basically the bipartisan infrastructure bill spending for hydrogen hubs, right?
Yeah.
So that's kind of fortuitous timing. We did not foresee that coming, but here it is, and we're working as fast as we can on that to get that work rolled out and published, get some results there.
So when you were dealing with the Department of Energy, did they have specific questions that they wanted answered? Did they just kind of let you take the lead on how you're going to model out your hydrogen infrastructure in the study?
Yeah, so yeah, they always they have their targets and goals in mind, right? For sure. They do a lot of work, their labs. And, as I said, they wanted to, one of their emphasis with that particular funding opportunity was data centers. So we tried to listen to that and respond to that. But when it came to like our project demonstration and even the modeling side, one of the metrics we're being judged on is the cost of hydrogen that would feed a vehicle, the cost of hydrogen at the dispenser. So, a lot of their research shows that kind of an ultimate target or goal would be $4 per kilogram. And maybe that's quickly changing in today's energy landscape. Maybe that's more like $5 per kilogram. So that's an example of something, right? They do set up metrics and milestones for us to have to achieve, and that's a particular one there, right? So through the demonstration, all the cost, of operating that system, are we going to be able to deliver effectively $4 per kilogram to the Mirais?
Yeah.
And that's going to be kind of hard, right? If you take today's cost of all that equipment.
Right.
And then on that beyond part of the project, we for shorthand call it the Port Houston model or Port Houston study. That was one of our early metrics in the first year of the project, which we just wrapped up this past January, was to show a pathway for $4 per kilogram at the pump for, say, fuel cell trucks. And, the model shows that right now today, in Texas, we're estimating you're not going to be there. You're going to be double that in most locations of Texas. We're getting some advantages in that we are close.
When you're at in California at 16.
Oh yeah.
Yeah. Not bad.
No, exactly. Yeah. So that, $8 give or take. And, and that's really the cost. That's not maybe necessarily the price somebody's going to charge you for it, right? But we get some benefits of the local infrastructure, right, that we already have here. Also, making hydrogen from electrolysis and the ERCOT grid is cheaper than California electric rates, for example, and much of the world. So there are some cost advantages in Texas just right from the start. But to get to that $4, right, there's going to be, advances in technology, with, the efficiency of the electrolyzers or whatever, economies of scale that bring down the cost of the system. And then really maybe at the end of the day, it's policies or some type of policy might have to close that gap. And those policies are being proposed today, right? There's $3 production tax credits being proposed. Hopefully those get passed. But if all those things or some portion of all those pathways line up with reasonable kind of assumptions on improvements in technology and cost, we do see there's a path to getting to that $4, and that's what we showed DOE through that analysis back in January as we were crossing over, ending that first year and moving into our second budget period.
Now, fingers crossed. I think you'll hit that number, and there's also new material discoveries for fuel cells that can also lower the cost. I think there's a lot of opportunity to get those initial costs down outside of just economies of scale and government intervention too. So we'll see how that plays out. So we talked a little bit about the hydrogen that you're making now, where you're thinking it might be going. What are your thoughts on the distribution capabilities of hydrogen? Do you see delivery methods like pipelines, or a combination of pipelines, trucking, modular units being set up on location? I'm also curious about your thoughts on our ability to convert the existing natural gas pipeline infrastructure to use it for hydrogen. Is it a good use of our resources to just blend it? Should we revamp the entire infrastructure to make it more hydrogen friendly? What are your thoughts on that?
Okay, well, there was a lot in that question.
It was a bit of a loaded question.
Yeah. So maybe we'll go backwards with it a little bit on the, blending into the gas pipeline network. I think that's very interesting. There's potential there. There are also just a lot of questions there, right? And to what degree we can do this. And, this is definitely not an area of my expertise, the natural gas pipeline network. But the more I work on this project to learn about it, there's so many different types of pipes, so many different materials, the age of them, everything. It's a complicated, it's an aging system. To what degree we can just put some relatively high concentration of hydrogen in that pipeline network, I think is largely to be determined. There's still research needed in that space. It could be a great way to quickly decarbonize, but I think you might want to be smart though too about, if you're going to do that, what part of that distribution system you're going to do the blending in, right?
Yeah.
Does it really, do you focus more on just industrial end cases or end users? Do you need hydrogen pipe to your house, for example, if your home runs on natural gas? That in itself is a pretty controversial topic to begin with, right? There's a good case to be made for electrifying homes entirely. But yeah, that could be very interesting. I'll say one thing that we've looked at with respect to this is maybe an end use application of blending. We have a white paper that we published on this as in support of kind of the Port Houston modeling work, right? As we're not ready to publish our full findings there, but we've been publishing small snippets in white papers over the past year. But one of those was looking at blending hydrogen into the natural gas feed to a natural gas power plant, right? Yeah. But in that case, we said, this is a great application. There are a lot of unknowns and uncertainties around how you blend hydrogen with the natural gas pipeline network and whether or not you can use it. But we know in the Port Houston area right now, in the Houston Gulf Coast region, there's an extensive network of hydrogen pipelines, and a large percentage of their gas power plants are in a very close proximity to those hydrogen pipelines. So we took a step back and said, hey, let's, in the near term, right, we're trying to focus on what makes sense in the 5 years to implement, right? What some of this modeling effort. Well, in the near term, we don't have to worry about blending in the entire gas network. Mm-hmm. Let's just run a spur line from these gas power plants. And a lot of them are located within 5 kilometers, so it's not an unreasonable distance to cover. Yeah. And what are the impacts and costs associated with that? If you start blending 5%, 10%, up to 30% hydrogen, mm-hmm. What does that mean for CO2 emissions? And, obviously, you're going to pay more for that hydrogen because it is more expensive than natural gas. Yeah. That hydrogen does also have to come from a clean source, right? If it's business as usual gray hydrogen today, it makes no sense. The emissions are greater. So we do have to find that source of clean hydrogen. But that's an easy pathway to quickly have a big impact on CO2 emissions in the Houston area. A 5% blend is something like removing 500,000 cars from the road effectively.
Yeah, it's not insignificant.
And that's just 5%. And all the gas power plants there today likely can take that blend right away. You don't need to upgrade the turbine technology. Yeah. Now, if we start talking about 30% blends, now you need a new gas turbine more than likely. But at 30%, now you're removing like 2 million cars from the road in the Houston area. And there's only like 11 million registered cars in Houston. So that's a big percentage of the cars. So there's a great opportunity for doing that blending, and there's a great case to be made. Now, how about the whole pipeline network? I don't know, but in the near term, we can start, doing this in the end applications where it makes sense, where some of this hydrogen infrastructure exists.
Well, that really does go to something that I talk about a lot, and that's I like the thought of this as an energy transition instead of a light switch. Mm-hmm. And so it's little things like that really do add up to a big difference.
Right.
And that's where I think that a lot of the industry should start looking into are these small little changes.
Right.
The 5 to 10% blending. It's a big, it's a small add, but it can really add up in the long run. Mm-hmm. So I like hearing answers like that to really promote that transition idea.
And the other cool thing that result about that particular paper was, I think shortly after we published our white paper, I think it was Stanford did a publication. They published a study of looking, if you took all the natural gas out of homes in the U.S., what does it mean for emission savings and so forth? And if I remember correctly, the equivalent number of cars, let's just put it in that kind of context, was about the same. But that's like all the homes in the U.S. getting rid of natural gas versus just this one little region of the power plants. But those power plants, it makes sense, right? You don't consume nearly as much gas at your home. It takes a lot of homes to equal a power plant, right?
Exactly.
But you could focus on one small region and have a super great impact versus trying to do something very large scale and electrifying all homes, right?
Yeah.
But it goes to your point of a transition, right? You can take steps along the way as we're working towards the eventual end goal here. And I guess going back to your question about hydrogen transmission or distribution, to what degree you can blend is an open question right now. There's research. To what degree you can repurpose pipelines. My understanding is there is a error of pipeline in the ground right now that would be suitable.
Yeah.
But there are a lot of errors of pipe ground, like, I don't know, a pipeline installed in this decade versus the other that is just a slightly different material. Mm-hmm. So I think, there is an opportunity to pick and choose, and can you piece together the right era of pipeline and make a network quickly. The alternative is just building dedicated pipelines. But something we've also looked at, another white paper study, we kind of had this question, how do you do this distribution? And of course, there's trucking as a pathway, but typically it all depends upon the distance and the quantities, right? There's a point where gaseous truck delivery makes sense, where liquid truck delivery makes sense. But at some point, if your quantities are high enough or distances are long enough, the pipeline is the more cost-effective method. But a question we had in doing the Port Houston study part of the project was, how will we make green hydrogen for that area, for that region, right? Mm-hmm. How do we clean up the hydrogen? As I said, with the gas power plants, it needs to be clean hydrogen.
Right.
So what would you do for electrolysis? And, the first thought is a power purchase agreement with the wind farm in West Texas. And we make the hydrogen locally in Houston with electrolysis, and it's green. Even though you're still connected to the grid, but you put in the PPA, and you can get the green credit for it. And that's just, I don't know, intuitively, naturally, that's kind of what we thought made sense. But then we started questioning, well, maybe it's cheaper and easier to put an electrolysis facility out in West Texas. But if you do that, okay, now you need a hydrogen pipeline. But we dove into the economics of that and capacities and efficiencies and all, and published a white paper of these results. But effectively, it is more cost effective, we believe, to invest in that pipeline. Now,
really?
Of course, that's long term, right? Big picture down the road. Near term, no, right? For one electrolysis facility, putting in a big pipeline is going to make sense. But, if you could fill up that pipeline, right, to capacity, effectively, the cost of a pipeline from West Texas to the Gulf Coast region is about the third of the cost it would be to put in the number of electrical transmission lines and corridors from West Texas to Houston to power that electrolysis equipment. So the two models are, you generate the power in West Texas and do electrolysis on site and then pipeline hydrogen, or you transmit the electrons from West Texas to Houston. And it was kind of a surprising result, right? I think intuitively I expected the electrical transmission to be the best path forward. Yeah. But one of the kind of the discriminator there is just really the energy density of the two methods of transport, the power line versus the pipeline. Because it's not just one pipeline versus one power line. If that was the case, or that the power line would be more cost effective, but it's actually one pipeline versus 5 electrical transmission corridors. So,
especially with hydrogen being so low density.
Right. And you still have it in that pipeline at several hundred, maybe 1,000 PSI.
Yeah.
Just like all the pipelines today are. Mm-hmm. But that's the discriminator. You just need a lot of copper to transmit the amount of electricity you would need. So you're kind of better off just keeping the electricity out there and converting into hydrogen and transporting it that way. And if that were to ever happen, right, that pipeline doesn't have to be just green hydrogen, right? Now you can look at that same model for SMR-based hydrogen. Yeah. Why put all the natural gas in a pipeline, send it to Houston and make hydrogen down there? Maybe it makes sense to make the hydrogen in West Texas, and now that pipeline is hydrogen. At least it's a cleaner gas, right? If it leaks, that's a whole nother controversial topic as well. I don't know if we want to get into that, but on the surface, one could say it's better than leaking methane. But recent EDF reports or studies are questioning that due to hydroxyl radicals and things that
Yeah, we'll
kind
see
of
what
hydrogen can
happens
have a
with
secondary
studies.
effect for greenhouse gas emissions. We'll see how those studies all pan out. I think there's a lot of research should be done there
Yeah, I
to
do too.
address those questions. And they bring up valid points, but we gotta investigate all that further. But anyway, if that pipeline were in place, you could be making hydrogen from various forms using all the resources in West Texas. Get it to the Gulf Coast, and not only can it supply that industry that's already there in the Houston region, but we're already a big exporter of energy, right? Port of Corpus Christi has LNG terminals for exporting LNG, right? Suddenly we're setting ourselves now up to even be big exporter of hydrogen to the rest of the world, or East Coast, West Coast, whatever it might be.
So we had talked briefly, and you had mentioned briefly about some of your partners and some of the backers that you have. From what you said, what I understand, Frontier Energy, GTI, Texas Gas Service, SoCal Gas. You mentioned Toyota, Shell, Mitsubishi Heavy Industries, Air Liquide, Powercell Sweden. They're all involved in this project?
All those people are involved, and then some. I almost hate to start listing off everyone, but Chevron's has joined our project. Conoco Phillips. Those are two examples of oil and gas companies that recently formed low carbon teams, right? Which is a shift.
More jumping on that ship too.
Yeah, a shift for that entire industry. And as in developing their low carbon teams, hydrogen's part of that mix, right? And they wanted to join onto the project to learn from us, maybe even expand our scope a little bit of things that we're looking into, maybe with their particular business interests. But the crazy thing about this project is we proposed it in 2019, May 2019, I think was about the time frame when we turned in this proposal. Hydrogen was the thing back then, but it wasn't as hot as it is today, let's just say.
Yeah.
We were given our award notification in August of that year of 2019. It then took us about another year to get under contract with DOE, which is just typical. That's just how it works. But over that next year, the buzz around hydrogen changed like instantly. As soon as we got our award announcement, we had industry partners calling us up, wanting to chat, wanting to learn more about the project. And I think it was the aspect of it being done in Texas that was the exciting thing to these folks. So these are all
in everyone's backyard.
Major players in the hydrogen business or in and around it in some manner, right? We have partners now on the industry partners on the project that are covering the entire value stream of hydrogen, right? From production to the distribution to the end uses to people making the electrolyzers or the fuel cells or what have you, right? Mitsubishi Heavy Industries was one of our first partners to join after the fact, right? After we got the proposal award. Some of our partners were on from the beginning. Waste Management, One Gas, Toyota, Air Liquide was on from the beginning, but Mitsubishi came on afterwards. They wanted, and they're involved in all sorts of things with hydrogen business, right? Whether it's electrolyzers or gas turbines that can run hydrogen blends. But they wanted to be, they have a headquarters in the Houston area. They think there's big opportunities for hydrogen in Texas. I mentioned we're using a wind farm in the demonstration part of the project. Well, they came on board and said, hey, rather than using somebody else's wind farm, why don't you use ours? We have an asset in West Texas. We'll provide you the data from that wind farm and let you replicate that for your demonstration project. Also, we'd love to understand more about how that wind farm asset could make hydrogen, use hydrogen. What role would hydrogen have for it? That's something that they were interested in. So that's been part of the modeling side of the project as well, is taking a dive into how does a wind farm make hydrogen and use hydrogen or sell it or whatever the case might be.
Yeah.
But we even have a partner on the project, McDermott International, who's basically, they're the guys, you need a refinery built. They're the ones that go build a refinery, right? So they're looking at this like, well, our next refineries are going to be hydrogen plants.
Yeah.
So they're coming in just to learn from the project. And all these partners are bringing funding to the project to help support our activities, help. Most DOE projects like this require cost share, so they're helping us satisfy the cost share, the cost match to the project as well, which we're very grateful for. Chart Industries is another one that joined, right?
Yeah.
So they're in the liquefaction business of natural gas. Well, their next business is liquid hydrogen, right? So they're already doing work with liquid hydrogen tanks and how you might distribute it. So they're a big part of the project too. And what it's also been great for the project on that, especially on that modeling side, is having all these partners throughout the entire value stream of hydrogen. Is, that model is only as good as the data we have going into it, right? At the end of the day. So it's providing us a great network to vet our assumptions against, how we're building the model, but the cost metrics or efficiencies or any of that. So they've all been very willing partners there in helping us make sure that it's a realistic model, right? Sometimes, you build models like this and thinking like an academic here or whatever. The engineer working on this for us, he's the one who pointed it out to me, so I have to give him all the credit. His name's Josh Rhodes. He's like, you go build a model and you have to go find a reference for your inputs, and then you try to dig into where their references came from, and it came from the previous version of that same report just 3 years earlier. Then you go look at that one, and it's from the report 3 years prior to that. So having the industry feedback into this part of the project, I think, is going to be very valuable. Helps us gain more confidence in the results that we'll be seeing from it.
That's great. And as we wrap up here, I've got one more question that I'm really interested to get your insights on. But before I do that, there's news blips coming out every now and then about different nations setting up their own hydrogen hubs and how it's supposed to look. I have never heard or seen anything as comprehensive as this one. That's, I think, one of the reasons why I'm so excited about it. I'm so glad that it's this kind of in our backyard here and we're getting it moving forward. But I've never seen any other hub announcement with so many partners involved, so many different industries getting involved. We're talking about hydrogen liquefaction partners, oil and gas entities, renewable energy. Everyone's coming together, and it's like this kind of nirvana approach to the next energy phase. And I just want to give you my congratulations for setting up such an amazing project.
Thank you. Yeah. Well, we're very excited about it. I don't know, kind of right time, right place, maybe in a way. I think there's one thing this project also has done, has brought together all these people, but with, these upcoming hydrogen hub opportunities and announcements, right? Yeah. It's just giving a lot of visibility to Texas. That was our hope when we wrote the proposal. I think DOE's hope too was in funding it, that it would get this interest really spawned in Texas. And I think it did from that perspective. I believe they're just as proud of the project as well, and the amount of industry interest that it's generated. And it'll be very interesting to see how things develop over the next year or several years, right? Maybe the next 5 years as different hydrogen hubs are announced throughout the country. And the crazy thing is, we didn't realize we were working on a hydrogen hub project at the time, right? It's just we were in a way, I kind of laugh about it. It felt like we're a little bit ahead of the game in developing this project, right? But then suddenly now the game is like way outpaced us in a way too, right? So we're, as I mentioned, we're year one in the project. The modeling side of things, we hope to wrap up by the end of this year and get a report out on that. We do have a lot of white papers that we've published, a handful of those already sort of related to the projects. Those are if you just Google H2 at UT, you'll come to a university-wide website with a bunch of hydrogen researchers. There's a featured publications link or something in there.
I was going to ask where people can find your findings.
Yeah. So just Google H2 at UT, it'll pop up and you'll be able to browse that site. And then there's a lot of information of other researchers and things going on at UT in the hydrogen space that don't necessarily involve us. The Bureau of Economic Geology is a big one, right? So these are the guys that know underground storage, oil and gas reservoirs and everything. Mm-hmm. So they're forming an industry-led partnership group right now to look at the opportunities for hydrogen storage beyond just salt domes, right?
Yeah.
How do you look at what other types of basins make sense, depleted reservoirs or whatever the case might be? And Texas is rich with all that for sure.
Sure is. So the last question, and I ask everyone this, and I think you're uniquely suited to have a very good viewpoint on it. What's your vision of the future for hydrogen?
That's a tough one, right? Like how far in the future, right?
Yeah.
I guess I just come back to it. I think its future is it's an energy carrier, right?
Right.
I think quite simply, it's an energy carrier. We want to meet all of our goals by 2050 or whatever the date is for your CO2 emissions goals, right?
Yeah.
Fight global warming, climate change. I think hydrogen is going to be a part of that, right? All of our power generation, as we go to renewables, right? Everyone knows about the temporal variations and how do you balance power, and right, California has a problem with too much renewables being generated at times and just kind of wasting power. And if it's not hydrogen, I don't know what it is that is capturing that energy. And it could be batteries, right? Batteries, I think, are a much lower scale. But I think about, like, how do you capture the breeze? How do you capture sunlight?
Yeah.
Bottle it, right?
And store it
and
for a
ship
long
it
period of
elsewhere.
time. Yeah.
And not just bottle it and use it there, but bottle it and ship it elsewhere, right?
Right.
How else do you do that if it's not hydrogen? So that's kind of how I see it. And I say hydrogen, that could also be ammonia. It could be methanol, right? It could be a bunch of different carriers once you get it kind of to that hydrogen point. But it's that energy carrier. It's how are you going to capture that sunlight? How do you bottle it? And I think that's our best answer at this point. So that's what I think its big future is. And then once you have that, where do you use it? Where does it make sense, right?
Yeah.
I think gas turbines for power generation is going to be a path. Lots of industries that need heating, right? Steel, cement. If you can get that cost down and make it affordable, then you offer this opportunity, this new energy carrier, effectively, to be a new fuel for different applications. Where does it go in transportation? That's a little iffy, right? Right now, it makes a lot of sense in heavy duty, maybe less so in light duty. But if heavy duty ramps up and brings up economies of scale, maybe we all want to start driving fuel cell vehicles and forget about the battery vehicles. They become a thing of the past.
Yeah.
Although it only takes the next latest and greatest battery to change all that too for transportation, right?
Yeah.
So that's a big unknown. For me, I think the idea that I always come back to is just how do you capture that breeze or the sunlight and export it across the world?
I love that. How do you? This is how we bottle sunlight. I love that.
Yeah, so that's what I see the future of hydrogen. It's that or a bunch of electrical transmission lines.
I like hydrogen better.
Yeah.
Transmit that. Awesome. This has been an incredible conversation. I'm so appreciative for the time and effort that you put in to helping to create this blueprint, shaping the future of the hydrogen economy. Thank you for taking the time with me today. I really appreciate it. I look forward to hopefully having many more of these conversations.
For sure. Well, hopefully, maybe we can do something in person when the demo's up and running, or just maybe a follow up when we publish a report on the modeling side of things.
We'll be there.
All right.
All right, everyone. I would like to thank Mike for joining me today to discuss his views on the hydrogen industry. He is an absolute wealth of information, and we are eagerly awaiting the H2 at Scale report to be published so we can discuss it more on the podcast. Thanks again. I hope you all have a great day. Take care. Thanks again, Mike.
Thank you.
Hey, this is Paul. I hope you liked this podcast. If you did and want to hear more, I'd appreciate it if you would either subscribe to this channel on YouTube or connect with your favorite platform through my website at www.thehydrogenpodcast.com. Thanks for listening. I very much appreciate it. Have a great day.